Log on, tune in, find out. Another good idea from Cambridge.
That he agreed to come here. As for input design for dynamic systems, the history started by works of Mera, by works of Goodwin and Payne, and it had its down and ups. Here we have the man who revived this domain in recent years. There are a lot of things which happened. You can observe this at control engineering conferences. So, Håkan Hjalmarsson from the Royal Institute of Technology in Stockholm.
Thank you for this very kind introduction. I would first like to, of course, thank the organizers for inviting me. It's very inspiring to be part of this, and I'm also very much looking forward to the feedback I hopefully will receive on this talk. In fact, I'm also a bit scared because it might be that you already know everything I'm going to tell you, so it's like taking a step over the cliff here and giving this seminar because I don't know this audience. But in any way, please, whenever after the seminar, please corner me and come with comments and questions. So I'll be happy to talk with any of you. So I will talk about applications-oriented experiment design for dynamical systems. So firstly, just some acknowledgement to my former students, present students, and some other collaborators that have contributed to what I'm going to present. I will start with formulating the problem, and then I will discuss some computational issues, how to implement this in practice. Then I will discuss more, perhaps more interesting topics like what happens when we have complex systems, and also the added value of experiment design for the entire identification problem. Okay, so I'm from the system identification community. So for those of you that don't know this community, you could see it as a sub-community of the control community. So the focus is pretty much on control applications, but there are also a lot of other things being looked at. The community works mainly with theoretical problems. So if you go to one of our conferences, you would hear talks dealing with prediction error, identification, subspace methods, closed loop identification, experiment design, nonlinear models. And as Darius mentioned, the history of experiment design in this area goes back to the start of the 1970s with work by Mera, Goodwin, Payne, Sarup. So there were scalar criteria like we have heard during this week, the optimality and so on, often not involving then the application directly, more general type of criteria. And one realization was this, that the insight was that you could generate all covariance matrices by sinusoidal inputs, as Luke mentioned earlier on today in the morning. Then in the mid-80s, there was some renewed interest, mainly due to some new expressions for the variance of frequency function estimates. And then there could be more theory developed based on these expressions for experiment design. And then in like 10 years ago, there started to be a renewed interest again, and mainly I would say due to the advances in convex programming. And also some new concepts like least costly identification, where the focus is to perform an experiment that is as cheap as possible, subject to some quality constraint of your model. So it's a bit like turning things around, the constraint and the cost function. So that's the sort of current, the history here, very briefly. So I will start with an example, and being from the control community, I use a control example. We will look at model predicted control. If you don't know what that is, doesn't matter. It's just a control algorithm. And here we have a motor, an electrical motor with an electrical part, resistance, inductance, generates some torque here Here is the moment of inertia of the shaft. We have a gearbox, and here is the load that is attached to the motor. So it has some, the shaft here has some elasticity, and we have a moment of inertia here. And the objective here now is to control the input voltage such that we position the angle accurately. So we have a number of model parameters. I will call them theta. In this case, we have, for example, these things here, and we'll denote the true parameters by theta naught. And now, if I had access to the true parameters, assuming that the model I gave on the previous slide can really represent the true system, I would of course use those parameters in my controller, in my control algorithm. And then if I want to do what we call a step change, going from one angle of the motor to another as quickly as possible, I would have perhaps this response. So that would be the ideal response, the best I could achieve. Now, in practice, I don't have access to theta naught, so I will have some other parameter theta. And I will use that parameter theta in my controller, of course. And then I will apply that controller to the true system, which is governed by theta naught, the true parameter vector, of course. But then I will not achieve the ideal response when I apply this controller based on theta. I will get something else. So there will be a difference here. And now the idea here in my talk is to measure the quality of this parameter by the deviation between these two curves. So I introduce what I call the performance degradation. It's some kind of measure of the difference between the ideal response and the achieved response. In this case, it's just the squared sum of the squared errors. But it could be, this is just an example, so it could be anything. So I measure the quality of the model parameters by the degradation in performance I obtain as compared to if I would be able to use the true system in my application. So that's the key point here. And now the next key point is that I say, well, what are good and what are bad parameters? Well, any parameter that makes this small will be considered good. So I just sort out all possible model parameters in two sets. One for which this performance degradation is small, and one for which they are large. So I end up with a set here of acceptable models, being the set of model parameters such that the performance degradation is bounded by some value. And I will call gamma here the accuracy. You see, large gamma will mean a tight specification. So large accuracy would be a tight specification here. Okay. So here is an example then here with this motor, how this set can look like. Now I have many parameters I can only plot in 3 dimensions, so I just plotted for the elasticity here, for the resistance, and for the moment of inertia of the load, and then I get the set like this. So any model parameter in this set will give me an acceptable performance. So basically I don't care which parameter I have as long as it's in this set. So to summarize here, I introduced this performance degradation and the corresponding set of acceptable models. So what is now the purpose of identification? Well, it's very simple. I should produce an estimate that's inside this set. Then I will be happy, or the user will be happy. So it's perhaps a simplistic setup, but it's also conceptually simple, which is good, I think. Then I will introduce the concept called cost of complexity Q. And that is the minimum possible experimental cost required to achieve this objective. And that is in the spirit of this, what I call least costly identification before. And in this talk, I will take as experimental cost the output energy. And why do I use that? Well, we look in what's going on in industry. We have some constraint that when the variable exceeds a certain value, then the product cannot be used. And now the idea but often the yield is maximized by being as close as possible to this constraint. That gives us optimum, reward in terms of profits. Now, then we try to put the set point as close as possible to this bound. But then what we consider in the design here is not the set point, it's the variations around the set points. So if this curve here is the output. And then you see that, well, the smaller variations I have in the output, the closer to the bound here I can put the set point and the higher yield and higher profit. So it's reasonable to just consider the output. In fact, the output power, you could say, of output variance as a measure. I will use the output energy, which is just, of course, the power scaled by the length of the experiment, so it doesn't really change anything. So this leads to this problem formulation, that I would like to minimize the output energy subject to this constraint that my parameter estimate ends up in the set of acceptable models. Now I will be in a stochastic setting, so theta hat will be a random variable, so I cannot guarantee this. So I have to relax this problem just to say that, well, I'd like to have a probability that this happens, that it's very high. However, it's difficult to compute this probability, so we have to do some further relaxations here. And that brings me to computational issues. How do we solve this problem? So we look at three different relaxations. Firstly, the idea is to look at a standard confidence ellipsoid of our parameter estimate. So we have the probability that theta hat will be in this standard confidence ellipsoid will be 1 minus epsilon, with epsilon small. Then if we make the design such that this confidence ellipsoid is inside the set of acceptable models, clearly our objective will be achieved with at least this probability, even more actually, because they are not exactly the same. So the first relaxation is that we minimize the output energy subject to that the confidence ellipsoid, the standard one, is contained in the set of acceptable models. If we linearize that problem, we get this optimization problem. Minimize, I forgot n is the sample size. So I get minimizing the output energy subject to that n, the sample size, times r, where r is the per sample information matrix that Look also introduced, or average information matrix, is greater than the Hessian of the performance degradation function times a scalar constant which consists of the noise variance, the accuracy, and the chi-square quantile with n degrees of freedom, where n is the number of estimated parameters. So that's one possible relaxation. Another one is to use Chebyshev inequality with using the first moment of this function here, and we get that. And that leads us to this relaxation, that we should minimize again the output energy subject to this constraint, that the mean of the performance degradation is less than epsilon. And then if we linearize that problem, we have this. So now the constraint is that the trace of the inverse of the information matrix times the Hessian of the performance degradation is less than some number here. So that corresponds to L optimality, in fact. A third relaxation is to, instead of using Chebyshev bound, to use Chernoff bound. So this gives improved approximation, but I will not talk about this. It's just too complicated to discuss in this talk here. But you can find details in some paper. Here is the setup now. So until now, the presentation has been completely general. I mean, nonlinear system, whatever. Now to proceed, I will have to be a bit more specific. So we will look at discrete time, linear time invariant systems. Q that will appear is just a time shift operator. So the true system is assumed to look like this. So it's just a sum of, these are what we call the impulse response coefficients times lagged values of the input, and the same for the noise. The noise E here assumed to be white, but the H here gives some color to the measurement noise. We will use prediction error or maximum likelihood identification, so we form prediction errors exactly as Luke also described. We minimize, the estimate is obtained by minimizing this. We will assume that all signals are stationary and that the true system is in the model set, so that for a model structure there will be a parameter theta naught such that we obtain this model here. We'll also ask for high accuracy gamma, so that will mean that we'll need a lot of data, so we can rely on asymptotic properties. The next step we'll do now is to show how to convert these problems into convex optimization problems. So we'll just look at the relaxation 2 here, which was this. So what we do is we use Schur complements to rewrite the constraint here into the following form. So we get two things here. One matrix inequality and one trace inequality here, where M now is a new matrix. It's a symmetric matrix which with dimension equal to the rank of the Hessian here. And this quantity here is just the Cholesky factor of the Hessian of the performance degradation. So these are the inequalities that we have to satisfy. And by then if we look at the information matrix in our setting, as Luke also pointed out, it looks like this, where phi u is the input spectrum. So we are in this frequency domain design that Luke also explained. Psi are sensitivity of the predictors, but in the frequency domain. And what we do now is that we parameterize the input spectrum linearly. So for example, like this. In this case, so we use here a complex exponential as basis functions, and these will be our free parameters, these R's, that we will optimize over. So in fact, these are just the covariance function of the input that we are optimizing over. And then that yields that the information matrix is just a linear combination of certain matrices Rk, where these are free variables now. So then if we go up now to look at this inequality here, what we have is that this guy is linear in the decision variables R. These are fixed matrices. They only have to do with the application. And M is a free matrix. So this is a linear matrix inequality. And also here is a linear constraint. But then when I introduced this parameterization, I also have to require that we have this is a spectrum, so it has to be positive. So we also have to ensure this constraint. But then we can use what is known as the KYP lemma to show that this infinite dimensional constraint is equivalent to a new LMI. And if we look at the experimental cost, which we took as the output energy, it's also easy to show that this is a linear function in the decision variables. So if we put everything together, we have that this relaxation 2 can be written in this form. A cost that is linear in our decision variables, and then a matrix inequality, where the matrix is affine in my decision variables, the covariance functions, and some new matrix X, which is symmetric but completely free. And this is a semi-definite program. So it's a convex problem, so we can solve this problem using off-the-shelf software. Exactly. Well, I mean, within whatever accuracy we want. And this can be done for the other relaxations as well. We can also add constraints if we want. So for example, if the input spectrum is to be lower and upper bounded by some functions here over some interval of the frequency axis, we can use what is known as a generalized KYP lemma and convert these inequalities into an LMI as well. So we retain this semi-definite program structure. And adding constraints can be very useful. So here is an example. We have a mechanical resonant system, so it may be hard to see now. We have a peak here. This is a frequency response. So there's a peak here and another peak here. And in the design, there's a bound here on the maximum of the input spectrum. And the optimal design for this problem, I won't go into the details, is this input spectrum here, where a lot of power is put at the resonance. So you can imagine performing this experiment on some lightly damped mechanical structure. If it's a plate, it will oscillate like this. It will be terrible experiments. It will probably destroy the equipment. But then what you can do is just to introduce a constraint, an upper bound on the spectrum, and the new optimal solution, optimal input spectrum looks like this. So it suppresses the peak here, so it will be less oscillations when we do the experiment. So it's very useful. We can extend this to other parameterizations of the input spectrum. So we can, in fact, parameterize all possible information matrices, which may not be possible with the parameterization I showed you before. We can also design a controller jointly with the input spectrum. So we can do optimal closed loop identification, which is important in many cases in control. We can handle multi-input, multi-output systems. We can also add a higher order approximations rather than these linearized problems. Can also, as a look, I'm just referring to your talk all the time, looking at that, by noticing that the spectrum plays the same role as the probability density, we can translate this whole framework into nonlinear systems. But if you're looking at dynamical systems, I mean, the PDF is multidimensional then. So then we have to adapt to that framework. It's possible, but what the size of the problems we can handle is still quite limited. I give some pointers here that is at the end of the talk. So that is sort of the computational issues. Now I'll talk a little bit about how to implement this in practice. So we start with the ideal case, meaning that I assume I know the true parameter vector, which all the solutions depend on. So how would I do then? Well, I solve my convex problem, and that results in an input spectrum. Then what I do is I do spectral factorization. So I obtain a function RU here, which when I square it is equal to the spectrum here. And this RU can be seen as a filter. It's a stable, can be taken to be stable. So then what I do is, if I have this, if this is my system, I add white noise as input, but I filter it through this filter before I apply it to the system. And then U here will have phi U optimal as a spectrum. So it's very simple. Now in practice, we don't know the true parameter which we need in our experiment design, so we are led to some sequential or adaptive approach. So it's also very straightforward. We do recursive identification, so we produce an estimate theta hat as a function of time, and we use that in our experiment design as the true value, so certainty equivalence design here. And then we update our experiment design for every new measurement we obtain, or batch-wise if we want. And that gives us a sequence of filters that we then apply here. So what we have here now is a time-varying filter, because coefficients will change depending on theta hat. So it's an adaptive feedback system. So questions arises, of course, regarding convergence and accuracy here. And we can actually back up this now with some theory. So if you have an ARCS model structure, the true system is in the model set, and the system is stable, this adaptive procedure will converge to the optimal per sample information matrix when the sample size grows to infinity. So that's a form, and it's incidentally based on the result by Lai and Wei from '82. Not surprisingly. So now let me move over to some more conceptual points here. So let's look at complex systems. So as you all know, society is facing a number of grand challenges. So we have CO2 emissions that have been lowered, we have problems with energy, so we have to have smart power grids, we have to have intelligent buildings, we have to have intelligent transportation systems, and all our funding agencies are pouring money into this. And the solutions to all these problems are based on models. It's model-based engineering solutions. But these systems are very complex, many of them. So here is just a graph of the power grid, of the Nordic power grid, all the power lines, and this system consists of hundreds of thousands of states. It's enormously complex. And we need a model for this. But then the question is the experimental cost now for obtaining a model of this complex system to within an accuracy that is meaningful, is it affordable? And I have never seen anyone answering this question. So it might be that all these grand challenges are, we cannot do it, but no one has investigated this. So it gives us sleepless nights if you start to think about this. So I will try to, I will not cover the power grid here, but I have some thoughts on this, and I will introduce this concept of cost of complexity. So the idea is to quantify how this minimal experiment cost Q, that I called Q before, depends on the system complexity and the performance requirements of the application. And the focus in this part of the talk is on some insights. So I will look for explicit solutions or an approximation rather than just computing things numerically by the tools I've showed you before. So we will limit ourselves to linear regressions problem, although we can extend this to much more general forms. But and we will set the noise variance to 1 just for simplicity. So this is the system we will look at. So it doesn't look so complex, but of course there can be many parameters. So that's sort of the complexity that enters into this problem here. For example, the system could be a finite impulse response type. So a system of this type where n is finite can be written in this linear regression form, where the regression vector contains of lagged inputs, delayed inputs. And we will, as before, use the output energy as experimental cost. And in this case, we can write it in this form, where R now is the information matrix. It's then the expected value of phi times phi transpose, as you all know. So if I use relaxation 2, the problem I would like to solve is this. It's this coming from the Schur complement. So this is the problem. Now if we look at the inequalities here, we can show that this implies this lower bound on the information matrix. If we are to satisfy these constraints, this has to hold. And if I multiply now from left and right with theta naught, I obtain what I have up here. So I get an inequality for the cost. So I get this inequality. So it's theta naught times the Hessian times theta naught, but that's approximately the performance degradation evaluated at the origin, and then normalized by the accuracy over epsilon, which had to do with this probability that I want to achieve. So this is a general lower bound for the required output energy, no matter what, for linear regression problems. So let's go back to this motor example I had. In the set that I showed you, the set of acceptable models that I showed you before, the input move size was limited to 3. That means that for each time step, the input is only allowed to change by amplitude of 3. If I increase that constraint to 40, I can have a much more aggressive controller. I can change by 40 instead. So I can have a much faster step response, much more aggressive control. And you can imagine that requires then a more accurate model to get good results, and that is evidenced by this set here. So this is the set of acceptable models in this case, and you see that this set has shrunk. I can rotate it a little bit here. And what we see here, for example, is that the elasticity, which is in this direction, we have to have a much more accurate knowledge of that, and that's intuitively clear. So if I have a more aggressive control, it's easier that the shaft will start to oscillate because of the fast changes, and so it's quite natural. So what we see is that the performance specifications that I had, they are now implicitly in terms of this input move size, determine the shape of this set of acceptable models, but that's a function of the performance degradation. You see the contour plots are much denser here than here. These are contour plots for the performance degradation. So the curvature increases of this function when the specifications are tightened. And of course this is application dependent, but generally this is what is happening. So it could probably be a complete theory for how this works for different fields. And then since these changes, that means that the function value at the origin will increase when the performance specifications are tightened. So the lower bound will increase, and we can actually quantify that. So, but if we study this performance degradation function, we can quantify what is the minimal experimental cost possible. So it depends strongly on the performance specifications, and for a particular application we can try to assess what this value is as a function of performance specifications. So I think that's important engineering insight. So let's now look at a few different cases. First, let's assume that R is a free design variable, the information matrix. So we had these two inequalities, and now since I have complete degrees of freedom, I pick R to be equal to the right hand side here. Then if I plug in that R here, I achieve this lower bound. So in fact, if I can design the regressor vector completely freely, I do not pay any price at all for having many parameters. I achieve this lower bound, which has nothing to do with the model complexity. It only has to do with the sort of the intrinsic properties of my application, not on how many parameters I'm estimating. So that's really a good case. Now let's look at a case where the information matrix is tuplets. That happens when we have FIR, finite impulse response models. Then the information matrix can be written in this form, where gamma here is a vector of complex exponentials, and phi u is the input spectrum. And we will now assume that also the Hessian of the performance degradation is tuplet, so it's generated by another positive function here, phi performance degradation. I will show you an example later when this happens. So now if we go back to the original formulation of the second relaxation, which was this, and we let the number of estimated parameters grow. We are interested in when we have very complex systems. Then we can use the properties of the eigenstructure of this tuplets matrix and this tuplets matrix to show that basically this trace here is the sum of the ratio of the function generating the performance degradation over the input spectrum over a grid of the frequency axis. And then if I now assume that this function is positive in a certain set omega, which covers a fraction psi of the total frequency axis, which is from 0 to 2 pi, then if I normalize with 1 over xi n and let now the number of parameters grow, this will converge to this integral. So if I collect pieces, if I use that and that, I can then replace this constraint by this constraint. And then, so this is the problem we would like to solve now. But now, if you look at the cost function here, it can be written in this way. And if I take theta times gamma, I obtain the system frequency function. So I can write this now as this. So this is the transfer function or frequency function from the input to the output. And phi u is the input spectrum. So now for large model ores I have this problem to solve. And the solution is easy to obtain. It's given by this expression here. The corresponding cost, output energy, is given by this expression here. So the cost is proportional to xi times n. So xi we can see as the bandwidth of the application. It's the frequency range over which this function that generates the performance degradation is non-zero, and then n, the number of parameters. So if the cost is too high for a certain number of parameters, then what I have to do is to reduce xi. So I have to reduce my performance requirements in the application. So here's an example. This is another control algorithm, so it's called model reference control. And the objective here is to design the controller that sits here such that the or frequency function from the disturbance to the output looks something like this. So what it means is that we are trying to attenuate disturbances at low frequencies up to a certain bandwidth. And I can choose different bandwidths here, different desired bandwidths. So I have a desired sensitivity function that this is called the sensitivity function, the function from here to here. And the higher bandwidth, the higher xi, the more aggressive will my controller have to be. So I have to use more power here to achieve better attenuation at higher frequencies. Now I let my controller be a function of my model. It's actually a function of theta then. And if I apply that controller to the true system, I achieve this sensitivity function. So it's not the desired one. And as performance degradation now, I just take the relative error between the achieved sensitivity and the desired one. So this. And this is the L2 norm. So these are functions of frequency. So I integrate the square of this over the frequency axis from 0 to 2 pi. Here's a simple example with two parameter system. When I have low bandwidth, xi, the performance degradation looks like this. These are contour plots, and then you see that in this direction I have theta 1 here and theta 2 here. I don't have to have a very accurate model, but in this direction I have to have a pretty good model. And this direction corresponds to the sum of theta 1 and theta 2. So I need a good estimate of the sum of the parameters, and that corresponds to the low frequency behavior of the system. So I need, in this case, a good model of the low frequency behavior of the system. If I increase the bandwidth, the desired bandwidth, the level curves change into more circular ones, meaning that I need a good estimate of both parameters. So the entire frequency response is important here. So we see here how the performance specifications have an impact on what how the model should look like. Now the next question is then how the bandwidth xi influence my experimental cost. And for this particular control problem, we can show that indeed the Hessian here of the performance degradation is approximately Toeplitz, where the generating function corresponds to the spectrum that I will have at the input if I achieve my desired sensitivity. And this will increase if I increase the bandwidth, because then I will need more power to do this attenuation. I have not had time to go into the details of this if you don't know it from the beginning, but this is the case. So then the cost here, using the theory I showed before, can be expressed approximately like this. So in fact, psi here, the fact that I used psi was not a coincidence. It's the bandwidth appears here is the effective bandwidth of my problem, and times the number of parameters. So if I have many parameters but cannot use so much energy, output energy, I have to reduce psi. I have to reduce the desired bandwidth here. And here is just an example. So this curve here shows how the cost Q depends on psi. So of course I can compute this numerically and give a curve. So this gives us a trade-off, the user the ability to make a trade-off between performance and experimental cost. So this was somewhat depressing because here we see that the complexity plays an important role. So do I have any good news to come with? Well, if we take the case that we're looking just at the scalar quantity of interest of the system, and then we take our parameter estimate and plug it into this function that we are interested in as estimate of this quantity, and form this as performance degradation, just a squared error, then you can easily see that this corresponds to C optimality criterion. And now if I define the lambda k here to be the partial derivatives of my function of interest with respect to the model parameters, and define the Fourier transform basically of these partial derivatives, and it turns out that this is positive, then I can show that the optimal input from an experiment design point of view is proportional to this function. So it might seem like an odd result, but in fact this is very useful in some cases. And what it shows is that the same input is optimal regardless of the system and model complexity, because that doesn't appear anywhere here. And this is most easily understood by looking at a couple of examples. So if we start out with this finite impulse response system, and suppose that we're just interested in the sum of the impulse response coefficients, so the sum of the estimated parameters. Then partial derivatives with respect to one parameter here is just 1. And suppose now that n naught is very, very large, then when I compute the Fourier transform of a sequence of 1, I get a direct function at 0, which in the time domain just corresponds to a constant input. So it might seem very strange to use a constant input now and if I'm going to estimate many parameters, but the fact is I'm only interested in this sum here. And even though the problem will be singular, so I don't have a unique solution of my parameter estimate, I will get a good accuracy of the sum here that I'm after. So that's all I need. That's all I ask for, and that's what this algorithm gives me back. And then you see that, of course, if I use a constant input, it doesn't matter what n naught is, I still get the same result. So this is some good news. Complexity here doesn't play any role. I can estimate as many parameters as I want, even over parameterize. This is, it looks like a very trivial example. So let's take something a little bit less trivial. We have the same system, but let's now say that we are interested in estimating what we call a non-minimum phase zero. It's a zero of the system transfer function, which is outside the unit circle. And this has particular importance in control. No time to go into details, but this is an important quantity. It limits control performance. Then it turns out that the lambda k's, the partial derivatives, look like this. And if I take the Fourier transform, I get this. It's clearly a positive function. It corresponds to an input which is an AR1 process with a pole at the inverse of the zero here of interest. And if I use that particular input, I get the same accuracy of my estimate of zero, no matter what the order is here, and no matter what the order of the true my model is, as long as it's larger than n naught. So here is just a graph. First, here I estimate two zeros inside the unit circle, and if I go from model order 3 to 5, you see that my Monte Carlo realizations spread out much more than here. So here I don't have this property. But if I look at 2 zeros outside the unit circle and go from 3 to 5, I have the same spread here. And if I go to 10 and 20 and so on, I get the same. Now I'm coming to also another part of what I think is very interesting, and that's the added value of experiment design for sort of the entire identification problem. So we have heard in many talks during the week that the true system is always more complex than the models we are using. We also know that the model structure has an impact on the accuracy. We also know that we have to deal with model order selection. So can we get any insights into how experiment design influence these issues? And now I will use relaxation 1 of my design problem, which was to embed the confidence ellipsoid into the set of acceptable models which corresponded to this problem. And what I will do first now is to reformulate this inequality. And recall that in the beginning I defined the identification criterion as the variance of the prediction errors and subtracting away the noise variance. What you can show is that this relaxation, this inequality can be replaced approximately by this, where on the right hand side we have the performance degradation with some scalar here. And on the left we have the identification criterion. And this comes from the fact that confidence ellipsoids are just level curves of this function here. So why do I do this? Well, if we think about now this optimization problem, well, it will cost energy to make the identification cost large. So we'll try to achieve equality here in order to use as little power or energy as possible. And what does that mean? Well, the right-hand side, this function reflects the importance of different model parameters for my application. So this function will be very steep, sensitive to directions in the parameter space which are important for my criterion. And then I will have the same sensitivity in my identification criterion. So that, in fact, you can interpret as these important properties of my system, they will be clearly visible in my data. They will be easy to identify. But on the same argument, directions where the performance degradation is not insensitive, then this function, the identification cost, will also be insensitive. So in these directions, I will have a poor estimate, meaning that I don't also have to spend a lot of effort on having a good model structure that can model these directions well. So that simplifies my identification problem as a whole. And I will go through a few of these issues here. So firstly, we will look at the impact of experiment design on the required model complexity. So we go back to this model reference control example. So we had 2 parameters in our model. If I have low bandwidth, the performance degradation looks like this. So I don't need a good model in this direction, but I need a good model here. And according to this. And then by solving now this problem here, and if I plot the identification criterion, it looks like this. So you see that in this direction, I will not get a very good model, whereas here in this direction I will get a better model. So basically it means that it's almost sufficient to use a 1-parameter model when I have this identification cost. I will do pretty well. So I can just discard one of the parameters and I will pick up what is important for my application here. So I can use a restricted complexity model. There is a formal result that backs up these claims. So if I have a sequence lambda k such that when I take the Fourier transform I obtain a positive function, And now if I form a vector, a finite vector of these coefficients, and say that, well, if this is this linear combination now of my true model, the system parameter is my scalar quantity of interest, and I then take the corresponding linear combination of my estimates as estimate of this quantity j, then if I have picked phi u, the input spectrum, to be proportional to this quantity here, in the limit I will have a consistent estimate, even though theta, the model that corresponds to this might not be able to represent the entire system. And I will show you, illustrate this in two examples here. So recall first that from an experiment design point of view, under these assumptions, I had the results previously that said that the optimal input spectrum should be proportional to this phi in this case. So if I do the optimal experiment design, I get this into the bargain. I get consistency even though I have a simplified model. So we go back to our two examples. First, the static gain case. Well, if I use this optimal input that I said was constant, well, after the transient has died out, the system equation looks like this. It's a constant times the input, which is constant itself, and the constant is the quantity I'm after. So it's sufficient to use a one parameter model, which will then pick up the sum here that I'm after. So instead of having a n naught parameter, I can use 1. So this is the trivial case. If we go to the non-minimum phase 0 problem and use this AR1 input process, it turns out that if I use two model parameters, I will have a consistent estimate of Z0, regardless of what the true system is, order is. It's sufficient with two parameters. Here, the next thing I'd like to talk about is the impact of experiment design on the choice of model structure. And we will look at just an example here. Frequency function estimation. So the objective is, I started a little bit late. So the idea, the objective here is to have a good estimate of the frequency function over a certain frequency region here, defined by psi. And here's the true system. It's a first order system. And I will compare two model structures. First one is a Laguerre structure when I plug in the known pole, the true pole here. So I estimate one parameter. And then I use a 30th order FIR model. So it's a biased model and it's of high order. And if I ask my colleagues which one should give me a better result here, everyone tells me the Laguerre should be better. However, if I now use optimal input for these two cases and scale the power so that it's the same, then the optimal spectra look like this. This is for the FIR model and this is for the Laguerre. And then if I now do some Monte Carlo simulation, it turns out that we look at the distribution of the performance degradation. We see that for the FIR model, the high order model, I get a much better distribution here. It's much more concentrated around 0 than for the Laguerre. So in this case, when we use optimal inputs, it seems like the choice of model structure is less important. I think I will skip this with the AIC and conclude here with just illustrating the power here of experiment design on sort of the identification problem. Here is a system with a non-minimum phase 0 at 3. We have quite some dynamics, and we also have colored noise. I have a simple two-parameter model. I use this adaptive experiment design. And if I plot the estimate of the 0 of this model, which is this Z hat, it converges to the true value. and I can in fact back up that by a theorem. So it's sufficient, regardless of the order of the true system and of the noise dynamics here, a two-parameter model run in adaptive mode will consistently recover my non-minimum phase 0. And I think it's a remarkable result myself, I must say, because it's an adaptive system. We have arbitrary under-modeling, but we can recover what we have, can show consistency. And the proof is relatively simple also. So I just want to mention some applications that we are working on. Model predictive control that appeared in the beginning. We're looking also at channel equalization in communication systems, and we are starting to look into control relevant models for combustion engines. So what have we learned today? Well, I try to convince you that applications-oriented experiment design can be good. Probably you already think that. And it leads to this L-optimal-like design. So of course my hope now is that you will move from D-optimal, A-optimal into, of course, L-optimal. So please everyone say after me, L-optimal design. Well, I'm kidding, but I hope you have got some idea that this can be useful. I paid special attention to the quantification of the experimental cost as a function of the performance specifications of the application, of the model structure, and the complexity of the system. This is what I call cost complexity. And by doing this quantification, the user can make trade-offs between the experimental cost and the performance of their application, for example. And this cost we saw, we had two examples in the linear regression case. One where the complexity did not cost anything when we had free choice of our regressors, whereas in the tuplets case, it became very costly. We also realized here that the optimal experiment tries to match the identification criterion to this performance degradation using as little excitation as possible, meaning that we don't have to model directions in the parameter space that are not important for the application. So I call it the let the sleeping dogs lie paradigm, which simplifies, and that was illustrated here lastly with this adaptive problem, non-minimum phase 0 estimation problem. So this simplifies the problem a lot. And yeah, I also show that this adaptive design is a practical implementation. So in summary, we try to focus on the application. Thank you very much.
That experimental design for input selection has evolved very much since the time of Mera and Zaro. We are a bit late, but we have time for one quick question. Please.
In the simplest case, we know that the optimum spectrum is discrete. Yes.
Yes.
But you had some results on where the optimum spectrum was a continuous one. Is it related to the fact that you in fact, it's like if you set some constraints directly on the spectrum?
I mean, it depends entirely. Firstly, it depends on the parameterization I used does not, of course, cover sinusoids. So I get the continuous spectrum from that parameterization. I can use another parameterization. I can also use sinusoids in my parameterizations. But if as soon as I introduce some constraints, then the sinusoidal solution is not optimal. And also it depends on the cost, the cost you have. So of course you can generate all information matrices by sinusoids, but that might not be optimal from the cost that you have from that point of view. So it might be better with another spectrum.
Thank you very much.
Thank you.